Good afternoon. It's my great pleasure to give this talk to honor Professor Mehmet Tasdamir. I hope that I could have been there in person, but because of family health issue, we have to do this online. I think very highly of Professor Mehmet Tasdamir. He's an outstanding researcher. He's a very great teacher, and also his contribution to engineering profession in concrete industry in Turkey has been outstanding. I had a pleasure of knowing Mehmet when he was visiting Northwestern. When he was at Northwestern, he did just pioneering work on applying fracture mechanics to concrete. He also helped organize a NATO workshop on fracture mechanics. And I've been also very fortunate that Mehmet sent his students to work with me, and those students also are, many of his students are contributing significantly to the industry and the teaching profession. Today, I'd like to thank the conference organizer for inviting me. So today I'm going to talk about carbon capture and utilization in ready-mix concrete. There are two issues that ready-mix concrete and construction industry is facing. One, to the right, is that production of cement, because of calcination, produces CO2, and that CO2 emission can be as much as 8% of the total global emission. The second issue is the world population is increasing, and more people are moving to urban cities. So our challenge is that we will need in concrete for developing infrastructure in the urban cities. How to do it in a very sustainable way is the second issue that we are facing. And we can provide increasing global need of cement and concrete because it provides an opportunity for carbon capture, utilization, and storage. If you look at the hydration reaction of one of the main components of cement, tricalcium silicate, C3S, when it hydrates, it produces calcium hydroxide. And if you inject CO2, it results into very useful calcium carbonate in the hydration product. Our objective is how can we accelerate and maximize carbon capture to use in carbon-conscious built environment. So what we must do is to have carbon capture, utilization, and storage in each of the stages of concrete construction. Starting with cement, we should have carbon negative supplementary cementitious materials. Aggregates occupy 70% of concrete, and we can carbonate recycle aggregate to replace natural aggregate and sand. And sand, as you know, is a critically short supply worldwide. Drinking water that is used in concrete amounts to 6 to 7%, and we cannot afford to use drinking water for concrete, but we can use modified seawater and municipal wastewater. During ready-mix truck, we can inject CO2. However, we have to enhance CO2 curing by proper additives. For finished product, for example, curtain walls, we can use carbonated natural fibers rather than man-made steel, synthetic, or glass fiber. And finally, demolished concrete, construction demolition, either due to hurricane or due to man-made causes, We can carbonate this construction and mineral waste and produce carbon negative supplementary cementitious materials. Let me give you some examples. If you look at this, during carbonation, of cement during hydration, there are two mechanisms going on. One is the hydration of cement, as shown here on the top, and other is the carbonation. And carbonation produces two products, calcium carbonate and, very important, calcium silica gel. How to manipulate them, the both to reaction and the controlling coupling is a key thing. Now, how much CO2 we can absorb depends on the environmental factors such as temperature and pressure, CO2 concentration, and the material factors such as alternative materials that can enhance CO2 capture. Calcium carbonate has 4 morphs shown here to your right: calcite, vaterite, aragonite, and amorphous calcium carbonate. Calcite is the most crystalline, more common, it's stable. Amorphous calcium carbonate is metastable, but if you can stabilize it, then we will show you that it actually increases the mechanical properties of concrete. For example, if you can increase the amorphous percentage of amorphous calcium carbonate, as shown here, then you can see you can increase the flexural strength. So poorly crystalline calcium carbonate, in fact, increases flexural strength. So, as I mentioned, controlling this morphology of calcium carbonate is very important. Also important is controlling morphology of calcium silicate hydrate. This is more complex because CSH, even at the nanoscale, is very heterogeneous. For example, here are shown a nano indentation value using atomic force microscopy of calcium silicate hydrate. So challenge is how to control morphology of CSH and how to manipulate the coupling between hydration and calcium carbonate. So as I mentioned, we can control morphology of calcium carbonate by biopolymer. And so we did some tests where we carbonated it with additives of biopolymer and to see how much amorphous calcium carbonate and how much stable, we use this thermogravimetric analysis. And from this analysis, the results are shown here. So what's plotted here is what is the relative proportion of the so-called unstable or amorphous calcium carbonate for control specimen, which was half cement and 50% slag. So for control specimen, you get 20% of calcium carbonate after carbonation is amorphous. However, if you add 0.1% of polydopamine, a biopolymer, then you can increase that amount. It turns out you can also increase the amount of amorphous by adding nanocellulose fibers. And this increase is also mimicked in increasing compressive strength. For example, compressive strength after carbonation of control at different ages versus when you add 0.1% of polydopamine. And you can see we have increased compressive strength by 36%. So you have not only absorbed more CO2, but you have also, by controlling this, you have increased compressive strength substantially. So next I want to talk about different waste product you can use for carbonating cementitious material. One of them, most of you are familiar, is fly ash. So you can replace cement with fly ash and then see what happens when you carbonate. So when you use class F fly ash or low carbon fly ash, then after carbonation, there is not much calcium left. So you don't have this important binding glue, calcium silicate hydrate. However, with higher calcium content fly ash, you have sufficient calcium to produce carbonation and strength gaining CSH. So it's important to use high calcium fly ash for. I mentioned briefly before that we have a big issue of mining waste. We now dump mining waste as a landfill, and that can be a problem in leaching as well as the collapse of the this big dam made with mine tailing. But many of the mine tailing, after you extract mines such as copper, coal, what is left is the alkaline waste. So if you carbonate this alkaline waste, then you produce what I call negative SCM or supplementary cementitious material. One example is a red mud, which is a waste product when you mine aluminum. So when you mine aluminum, you have red mud, which has the composite mostly lime, silica, and alumina. So if you carbonate this red mud, and it turns out that when you carbonate it, you produce calcium carbonate. But as I mentioned, you produce this alkali silica gel, which is a pozzolanic material, and it produces calcium aluminosilicate hydrate. So if you replace cement, let's say with 20% of this carbonated waste red mud, then you can see that you can increase compressive strength over control. So you have not only captured carbonation, you have used a critically dangerous waste material and produced very useful carbon negative supplementary material as shown here. So you can add up to 20%. Recycled concrete aggregate. Recycled concrete aggregate has a very large potential. These are the statistics in US. And if you carbonate recycled aggregate, then it can replace natural aggregate. So to give you a backstory, when you use recycled aggregate to replace natural aggregate, it reduces the durability of structural concrete made with so-called RCA because of this porous layer that surrounds recycled natural aggregate. And so we want to solidify this porous aggregate. So if you carbonate this, then you have calcium carbonate, and so that densifies the interface. And in fact, what is important, that very fine aggregate, when you recycle fine aggregate, it also produces supplementary cementitious material. So the advantage of carbonating recycled aggregate, no more quarrying sand or natural aggregate, and also you have capturing the carbon. So here, for example, are the results shown, the work done by Professor Poon in Hong Kong. Is he carbonated different size, and if very fine size, you can see that it can absorb a lot of CO2 because finer the size, larger the surface area. Now, I talked about the mining waste, but you can, another way of controlling construction waste is a process called two-step extraction. And that process was developed by former student, Professor Kawashima at Columbia University and her colleagues. So what you do is, you, as a feedstock, you demolish concrete waste. And then use two-step extraction. First, you reduce pH, and that produces this silica-rich supplementary cementitious material. And then you increase pH, accelerate carbonation, and then they have shown they can produce independently each of the moles of calcium carbonate. And if you add this supplementary, I call it carbon negative cement material, then you can see you can increase the rate of hydration and increase, for example, compressive strength. So this is a very innovative, useful product where you take construction waste and with two-stage extraction, you produce supplementary cemented material and single mode calcium carbonate. We know that when we have a ready-mix concrete, when it comes back, you wash the ready-mix concrete and that produces slurry. Now, from the slurry, after you remove the aggregate, and then you take that slurry and inject it to CO2, then what you have is supplementary carbonated material leads to supplementary cementitious material. And this is indeed, we showed that the compressive strength of controlled specimen and carbonation of controlled specimen, and then with carbonation with this addition of supplementary cementitious material, that is carbonated waste slurry. So you got rid of the waste slurry and also you absorb CO2 and produce supplementary cementitious material. I alluded to nanocellulose fibers earlier. Nanocellulose fibers are available abundantly, waste material, and they can substitute man-made fibers. However, when we use natural fibers, they react negatively with hydration product, produce these cavities and reduce durability. But if you carbonate natural fibers, waste or otherwise, then they densify the interface and you not only absorb CO2, but increase the long-term property of product reinforced with natural CO2. For an example of this is a sisal fiber work done at Hong Kong University of Science and Technology, where they took MgO or reactive magnesia cement to replace Portland cement. And they carbonated it without sisal fiber and with sisal fiber. And you can see that with sisal fiber, you can increase the amount of carbonation quite a bit. And this is also shown here with 14-day compressive strength of this is a controlled reactive magnesia, and this is with the addition of sisal fibers. So natural fibers can, as I said, act in multiple ways. I want to talk about biochar. Biochar comes from waste agricultural products, a variety of agricultural products. If you just burn them as it's often done, then it pollutes the environment. However, if you burn them without oxygen, that is with pyrolysis, then what you have, you capture the carbon and what you have is biochar. This biochar is very porous material and people are talking about many uses such as internal curing. We wanted to see whether addition of biochar can increase carbon capture, and indeed it does. So here is how much CO2 you can take with a control mortar, and when the control mortar has a 1% of biochar and 10% of high calcium fly ash. And you can see you can double the amount of CO2 you can capture with addition of biochar. And this is also mimicked in compressive strength. So compressive strength of 3, 7, and 28 days of carbonated mortar, and here carbonated mortar plus biochar and fly ash. So you can see that you can slightly increase the compressive strength, but the main thing is that you have captured CO2 and use this a waste material called biochar. I want to talk about can nanomaterials help in carbon capture, utilization, and storage. As you know, many people have been working with nanomaterial, specifically graphene-based nanomaterials. And that includes carbon nanotube, includes graphene and graphene oxide. And people have shown that addition of this graphene-based nanomaterial, if they are well dispersed, they have many positive effects on hardened concrete properties. We have done a lot of work, for example, with very, very small amount of carbon nanotube, and it's shown a variety of improvement. So can graphene-based material also enhance CO2 capture? To examine that, we have been using graphene oxide. So first you have make sure the graphene oxide is very well dispersed, and then dispersed geo and cement. We made a specimen, and the cubes were then carbonated in 12% CO2 concentration. And we found that addition of this 0.05%, very, very small amount of graphene oxide. So cost-wise, it's very affordable. And you can see that we increase carbon capture by 30%. And in addition, graphene oxide also increases compressive strength. So here is the addition of, this is a controlled cement paste, controlled with addition of graphene oxide, but uncarbonated. With carbonated, you can see that over control, we have increased substantially the compressive strength. So very small amount of well-dispersed so-called geo can capture, enhance capturing CO2 and increase compressive strength. Why does it do it? Why does very small amount of geo enhances carbon capture? Well, there are two reasons. At least there may be many we are understanding. One is that when we add graphene oxide, then after hydration, the size of calcium hydroxide crystal goes down. The smaller the size, higher the surface area, more carbon capture. Another thing is the graphene oxide, because of COOX surface charges, it captures calcium. And that, of course, enhances carbonation. So graphene oxide can be very, very helpful, very small addition in carbon capture and improving long-term properties of concrete. So in summary, I think that carbon capture, storage, and utilization is essential for us to have sustainable use of concrete and ready-made concrete, especially when you use waste materials such as recycled aggregate, construction and demolished waste, biochar. Then you are doing not only capturing CO2, but also solving the critical issue of waste material. And I hope this gives you some idea of what we can do. And thank you very much.